Energy types and transformations. You need both of these papers. Cut the border off. Once you've done that, I'm going to start off with this one. Okay, pay careful attention. We're going to cut on the double lines. So we're going to cut off that first row along the double line. Alright, and a few lines down we have another double line. Didn't copy very well in these. Cut along right there. Only cut on the double lines. So, here's where you're going to cut. Now you're going to fold these in half. Fold along the vertical line. Fold along the vertical line. And then set them to the side. Actually, not quite yet. Once you fold along the vertical line, each one of those, you're going to take your pen or pencil and draw in the horizontal lines that you can see through the paper. Set them to the side. When we talk about energy, there are many different types of energy we're going to discuss. And we have this very important law of conservation of energy. That helps give us perspective on all the different types of energy. It states, the law, that energy is not created, nor is it destroyed. It is just transformed from one type to another. Okay? We don't make energy, we just transform energy. Of the many different types of energy, there's one that we're going to talk about. It's called mechanical energy. It's not technically a type of energy, it's a way of calculating energy, a way of calculating this law of conservation of energy. So that one little piece of paper you guys picked up, the total energy of a system, the mathematical analysis of energy conservation. All right, this is mechanical energy. So write on it, mechanical energy.
We paste it? No.
You will in a moment. Mechanical energy. The total energy of a system, or the mathematical analysis of energy conservation. If work is being done, there is mechanical energy. Okay? So, mechanical energy, here we go. Go ahead and glue that in right there. We'll get in a lot more detail on that later on, but I just want to introduce that idea right there. If we want to calculate the law of conservation of energy, we're usually using mechanical energy. Okay. Now draw a squiggly line across your notes. The remainder of the page we are going to divide right and left for a comparison, a T-chart comparison. On the left side, we're going to write potential energy. On the right, we're going to put kinetic energy. All right? All types of energy can fit into one of these two categories, either potential energy or kinetic energy. So what is potential energy? It is stored energy. Okay? It is waiting to be released. Dun, dun, dun. Kinetic energy is the energy of anything in motion. So if it's moving, we've got kinetic energy. All right, take your two piece strips that are left, open them up, find the shorter one that has 4 rather than 5. It says energy of position, energy stored in the object because of its mass, gravity, and height. And then stored energy in chemical bonds, energy is released when bonds break. Energy stored in the nucleus of an atom, tons of energy in the atom. And energy stored in a spring or elastic object. So, based upon those definitions right there, are we talking about potential energies or kinetic energies? Why potential? Because they all say we've got stored energy. Stored energy. Stored energy. Energy that's stored. Okay? So these, I'm going to glue in on the left. Potential energy. So let's talk about these individually. First one. The energy of position. Okay? That's the technical term, which doesn't make much sense, but when you explain it this way, that the energy is stored in an object because of its mass, gravity, or height. So imagine a bowling ball sitting on a shelf. Okay? Kind of uncomfortable to stand underneath a bowling ball sitting on a shelf. Would you agree?
Yes, ma'am.
Because it has the potential to squash you. All right? That is what we call gravitational potential energy. Gravitational potential energy.
That's the first one?
That's the first one. The second one, energy stored in chemical bonds. The energy is released when the bonds break. That includes food. So think about food. Think about a nutrition label. What thing on the nutrition label tells you about the energy stored in that food?
The calories.
The calories. Very good. So there's energy in it. Plants, well, that's food. It's got calories. Batteries. There's chemicals inside batteries, and they're waiting to release the electricity. Fossil fuels. What are fossil fuels?
Petroleum.
All right. Gas, gasoline, petroleum. Yes. Okay? Those also have energy stored in the chemical bonds. You have to burn the gasoline in your car in order to get the energy from it. Okay? So, what kind of energy do we call that? That's when plants and foods and batteries and fossil fuels. What do you think we call it?
Wait, I got it now. I know this. Natural something.
Chemical energy.
Exactly.
All right? Energy stored in the nucleus of an atom. There's tons of energy in the nucleus of an atom. We harness that through nuclear power plants and nuclear bombs. Big boom. All right? So that energy is called nuclear energy. And the last one, energy stored in a spring or an elastic object. So if I just have a good old plain rubber band, woohoo, whatever, I throw it at you, it's like, who cares, right? But once I take that rubber band and I stretch it, now I've added energy to it. So the process of stretching it, I put energy into it. And while it's stretched, that energy is waiting to be released. You agree? Stretch it, I put energy into it, and it's just waiting to be released. This is called elastic energy. They often call elastic potential energy.
Elastic?
Elastic. Elastic potential energy. Our kinetic energies. Within the different categories of kinetic energy, when we talk about, so the first one, energy of movement, anything moving, anything tangible. So I'm going to say tangible objects. All right? If it's large enough that I can put it on a scale, then we're going to go ahead and use this. We call it kinetic energy. All right? It's a repeat, but oh well. Okay? Kinetic energy is just general kinetic energy. Now, if we have energy from moving electrons, if I have electrons moving, it's what powers your electronic devices. And it comes in the form of lightning, comes out of your outlets in the wall, it's generated in a power plant. What do we call that type of energy? Electrical. Electrical energy. Okay? Heat energy, the end product of many transformations, the results of friction. So you rub your hands together and they get hot. All right, fire, increased temperature. What is the scientific word for heat? Thermal energy. Light energy or electromagnetic radiation, same thing. When it comes specifically from the sun, we call it solar, but it applies to light bulbs, glow sticks, and everything that glows. What kind of energy, does anybody know what we call it? It's called radiant energy. Last, the movement of energy through substances in longitudinal waves. Examples include music or echoes.
Music energy. Echo.
Sound energy. Okay? The last thing we're going to do, we're going to take this paper, fold on the vertical lines. So with this paper, easy way to do it. Flip it over. Face white side up. Fold it so you can see the pictures. Fold on those vertical lines so you can see the pictures. Fold on the vertical lines so you can see the pictures. Okay? Nope. We're going to leave it like that. And then you're going to take your scissors and you are going to cut along the horizontal lines to the fold. Once you finish cutting all those, we've got all of those cut apart like this. So this paper is to help us go through some examples of energy transformations. So we're going to start off with this one right here. So if you want to keep your journals open, page 30. All right, so you can look at the different types of energy there are. What kind of energy do we get out of an outlet in the wall? All right, so this is electrical energy. That's what we start with. And then it transforms when it goes into a light bulb to what type of energy? Radiant. So we get light. Light is called radiant energy. Okay? Now this is one of those old light bulbs. Okay? We have the newer light bulbs that kind of have that twisty design to them, you know? Kind of looks like that. What's the difference between the old light bulbs and the new light bulbs? What's so special? Why do we have these new light bulbs? Yes, they use less energy. They are what we say more efficient, which means you get more light for less electricity. Okay? So with these old light bulbs, only a small percentage, about 10%, actually went to making light. The rest of that electrical energy transformed into heat. What type of energy do we call heat? Thermal. So we would get electrical energy turning into radiant thermal energy. Now with the old light bulbs, it's about 90%, about 10% radiant, 90% thermal. With your newer light bulbs, it's the reverse. It's more like 90% radiant, 10% thermal. So the difference is significant. When you paid for your electricity to light your house, 90% of it was spent actually heating your house, and of course you'd be paying for the air conditioning to cool your house. It was kind of ridiculous. So, more efficient light bulbs. All right, what kind of energy is the hamburger? Chemical. Any sort of food is chemical energy. It's energy stored in those chemical bonds. And when it gets into your body transforms that energy to help you run. What kind of energy is being used here? All right, we have kinetic energy. That's the primary use of energy right there. But our bodies are not 100% efficient either. If you're doing a lot of kinetic energy, what other energy is being produced? Thermal. You overheat when you exercise. That's why you sweat and all right? But the sweating is mostly how we cool off. So even our bodies aren't 100% efficient. Okay? Gasoline, what type of energy do we have in gasoline? Again, chemical. It is stored energy in the chemical bonds of the gasoline. You can leave it in the tank and leave it there for weeks and weeks and weeks, and the energy is still just sitting there waiting to be released, waiting for you to burn it. Put it into a car, the car burns it in an engine, and we get different types of energy out. What's the number one purpose of putting gasoline in your car? To make your car do what? To make it move, right? So what kind of energy is it? Kinetic. That's the number one purpose. But what else happens?
Thermal.
All right, the engine warms up. So we get thermal. All right? There's more. Give me another one. All right, we get light bulbs. You get a radio, maybe GPS system. I don't know, all sorts of electrical things in your car. There's actually what they call a catalytic converter in your car that does that conversion for you to electricity. And one that a student in my other class mentioned that I hadn't thought about, but is so true. Another not intentional, but natural cause of a motor running is sound. And sound is a form of energy. Now, unless it's a Harley, sound usually isn't the purpose, but you get sound out of it. Okay? So we get all sorts of energy happening, produced from this transformation. Okay, a battery. What type of energy does a battery have?
Chemical.
Again, it's chemical. It's energy that's been stored, and it's stored in the chemical bonds, the chemicals inside that battery. I remember as a kid thinking that batteries were kind of magical because there's like this little tiny, cylinder thing, and you can make your toys work. But there's actually chemicals in it. All right, we put batteries into a flashlight, and what kind of energy do we get out of our flashlight? What's the primary purpose of a flashlight? What type of energy do we want? Radiant. Now, when I was a kid, flashlights use a different light bulb than the kind of light bulbs we use now. Most of your flashlights today are LEDs, all right? LED bulbs, which is, I don't really call it that, but LED lights, okay? They use very little, these are highly, highly efficient. They use very little energy and produce lots of light. But before those, all right, before LEDs, your flashlights actually warmed up too. So thermal once again. Okay? You get some thermal energy there if it's not an LED. All right, sorry for the lovely little hand drawing over here. The picture didn't copy very well. What is this a picture of? The sun. What kind of energy do we get from the sun? All right, radiant. Okay? And you might run into that solar. Okay? It's a specific type of radiant, category solar. Okay, so like if it's coming from the sun, we call it solar. It's still technically a form of radiant. Now, on this one, I want you to draw a really long arrow. Really long arrow. Because we're going to label that arrow here in a minute. All right, what type of energy does an apple have? Chemical. It's food. All right? There's sugar in there. All right? There's sugar in that apple. Chemical energy stored in that apple. Now, here's a question that goes back to biology. You have a sun, you get an apple. All right? Obviously, you've got a tree there in the middle of the process, but the sun provides energy to the tree, and the tree can produce an apple. What do we call that energy transformation? It actually has a name. That specific transformation has a name. So think biology. Photosynthesis. Photosynthesis. That energy transformation is a very complex, important process essential to life. Leaves, very good. So we got a plant. All right, so what kind of energy is there in a plant? All right, it's a stored energy. We got a potential stored energy in plants. Which type of stored energy is it? Chemical. Okay, now again, a really long arrow on this one. All right, so the deer eats the plant. So we go from chemical energy to what kind of energy helps the deer run, run, run? All right, so kinetic energy. And because it's in an animal, we're also going to get some thermal in there. Okay, so that chemical to kinetic, that energy transformation of the body does getting the energy from the chemical food into kinetic and thermal, that energy transformation. Does anybody remember what that one's called? Cellular respiration. A process done in the mitochondria of the cells, by which glucose is turned into ATP. Okay, what's the picture of? Lightning and thunder. So lightning energy. What kind of it? Actually, let's go with that. Lightning and thunder. The lightning. What kind of energy is the lightning? Electrical. That electrical energy causes a burst in temperature change in its immediate area, resulting in thunder. What kind of energy is thunder? Sound. Okay, but what other type of energy can we get? If the lightning starts a fire, what kind of energy is that? Thermal. Am I zoomed in enough? Can you guys see? All right, next. What do we have a picture of here? A slingshot. Anybody ever played with one of these before? They're so much fun, aren't they? Kind of dangerous, but I grew up on a ranch, so it wasn't that big deal. There's always someplace I could go shoot around with one of those without damaging anything. All right, so what kind of energy do we use when we're using a slingshot? This type of slingshot. It's elastic. You pull back on that thing, and you put energy into the rubber band there, and you pull back. You put some sort of rock or something there, and you pull back, and you put energy into that elastic energy. Okay, and now this is the picture I couldn't find. Draw some sort of a rock, and then draw it flying through the air. Okay, so when you let that elastic energy go, it transforms, it makes this ball go flying through the air, or the rock going flying through the air. What kind of energy does it have when it's flying through the air? All right, we got kinetic for sure. And if you shoot it up into the air, what kind of energy, what other kind of energy do we get out of it? Yes, gravitational potential. All right, next. Does anybody know what that's supposed to be a picture of? Anybody know what that's supposed to be a picture of? Okay, think The Simpsons. Does that help? I know The Simpsons are still around. It may have come out when I was in elementary school, but it is still around.
A power plant?
Yes. What type of power plant? Nuclear power plant. Okay? So what type of energy are we starting with here? Nuclear. All right, now, this one has multiple transformations in it, so follow along, write small. We start off with nuclear energy. Okay? Nuclear energy, the first thing it does is it produces heat. So we get thermal energy. That heat is used in the power plant to heat water. That water, we'll just say the original versions of these power plants, produce steam. That steam would rise and turn a turbine. Do you have an idea what I say when I'm saying a turbine? Can I picture like a water wheel in a river? Does that make sense? Have you seen that before? Or like a windmill? That's a turbine. Okay, so what kind of energy would a turbine have? It's turning. Kinetic. Okay, and then that turning turbine is connected to a generator, and that generator then produces the final product that we want, which is electrical. Okay, so there's a whole series of energy transformations that occur to get the nuclear energy into the electrical energy that we want. Okay, last one. Not the best example, but I use it anyways. What kind of energy do we have in the process of juggling? Okay, we got a lot of them. So we've got kinetic and gravitational. Okay, and so kinetic makes it go up, and then once it's up, it's got lots of gravitational, and it comes back down, and then it gets thrown back up, and then it comes back down, and it keeps going back and forth, going up and coming down, and that back and forth process between kinetic and gravitational, this is where we get mechanical. We're going to talk about mechanical energy. Okay? So those are a bunch of examples of different energy transformations to help solidify in your mind this idea of energy transformations and different energy types.